G-force.
G-force is a measurement of acceleration felt as weight. It is incorrect to refer to it as a force, as G is an acceleration and can be measured with an accelerometer. Since such a force is perceived as a weight, any G-force can be described as a weight per unit mass. The G-force acceleration acts as a multiplier of weight-like forces for every unit of an object's mass, and is the cause of an object's acceleration in relation to free fall. This acceleration experienced by an object is due to the vector sum of non-gravitational forces acting on an object's freedom to move. The accelerations that are not produced by gravity are termed proper accelerations, and it is only these that are measured in G-force units. They cause stresses and strains on objects. Because of these strains, large G-forces may be destructive. Gravitation acting alone does not produce a G-force, even though G-forces are expressed in multiples of the acceleration of a standard gravity. Thus, the standard gravitational acceleration at the Earth's surface produces G-force only indirectly, as a result of resistance to it by mechanical forces. The 1 G-force on an object sitting on the Earth's surface is caused by mechanical force exerted in the upward direction by the ground, keeping the object from going into free fall. The upward force from the ground ensures that an object at rest on the Earth's surface is accelerating relative to the free fall condition, which is the path that the object would follow when falling freely toward the Earth's center. Objects allowed to free fall in an inertial trajectory under the influence of gravitation only, feel no G-force. This is demonstrated by the zero-G conditions inside a freely falling elevator falling toward the Earth's center, in vacuum, or, to good approximation, conditions inside a spacecraft in Earth orbit. These are examples of coordinate acceleration, a change in velocity, without a sensation of weight. The experience of no G-force, zero G, however it is produced, is synonymous with weightlessness. In the absence of gravitational fields, or in directions at right angles to them, proper and coordinate accelerations are the same, and any coordinate acceleration must be produced by a corresponding G-force acceleration. An example here is a rocket in free space, in which simple changes in velocity are produced by the engines, and produce G-forces on the rocket and passengers.
Unit and measurement.
The unit of measure of acceleration in the International System of Units, SI, is ms2. However, to distinguish acceleration relative to free fall from simple acceleration, rate of change of velocity, the unit g, or g, is often used. 1 g is the acceleration due to gravity at the Earth's surface and is the standard gravity, symbol, gn, defined as 9.80665 meters per second squared, or equivalently 9.80665 newtons of force per kilogram of mass. The unit g is not one of the SI units, which uses g for gram. Also g should not be confused with g, which is the standard symbol for the gravitational constant. Measurement of g-force is typically achieved using an accelerometer. See discussion below in measuring g-force using an accelerometer. In certain cases, g-forces may be measured using suitably calibrated scales. Specific force is another name that has been used for g-force.
Acceleration and forces.
The term g-force is technically incorrect as it is a measure of acceleration, not force. While acceleration is a vector quantity, g-force accelerations, g-forces for short, are often expressed as a scalar, with positive g-forces pointing upward, indicating upward acceleration, and negative g-forces pointing downward. Thus, a g-force is a vector acceleration. It is an acceleration that must be produced by a mechanical force, and cannot be produced by simple gravitation. Objects acted upon only by gravitation, experience, or feel no g-force, and are weightless. G-forces, when multiplied by a mass upon which they act, are associated with a certain type of mechanical force in the correct sense of the term force, and this force produces compressive stress and tensile stress. Such forces result in the operational sensation of weight, but the equation carries a sign change due to the definition of positive weight in the direction downward, so the direction of weight force is opposite to the direction of g-force acceleration. Weight equals mass x. G-force acceleration. The reason for the minus sign is that the actual force, that is, measured weight, on an object produced by a g-force is in the opposite direction to the sign of the g-force, since in physics, weight is not the force that produces the acceleration, but rather the equal and opposite reaction force to it. If the direction upward is taken as positive, the normal Cartesian convention, then positive g-force, an acceleration vector that points upward, produces a force weight on any mass that acts downward. An example is positive g acceleration of a rocket launch, producing downward weight. In the same way, a negative g-force is an acceleration vector downward, the negative direction on the y-axis, and this acceleration downward produces a weight force in a direction upward, thus pulling a pilot upward out of the seat, and forcing blood towards the head of a normally oriented pilot. If a g-force, acceleration, is vertically upward and is applied by the ground, which is accelerating through space-time, or applied by the floor of an elevator to a standing person, most of the body experiences compressive stress which at any height, if multiplied by the area, is the related mechanical force, which is the product of the g-force and the supported mass, the mass above the level of support, including arms hanging down from above that level. At the same time, the arms themselves experience a tensile stress, which at any height, if multiplied by the area, is again the related mechanical force, which is the product of the g-force and the mass hanging below the point of mechanical support. The mechanical resistive force spreads from points of contact with the floor or supporting structure, and gradually decreases toward zero at the unsupported ends, the top in the case of support from below, such as a seat or the floor, the bottom for a hanging part of the body or object. With compressive force counted as negative tensile force, the rate of change of the tensile force in the direction of the g-force, per unit mass, the change between parts of the object such that the slice of the object between them has unit mass, is equal to the g-force plus the non-gravitational external forces on the slice, if any, counted positive in the direction opposite to the g-force. For a given g-force the stresses are the same, regardless of whether this g-force is caused by mechanical resistance to gravity, or by a coordinate acceleration, change in velocity, caused by a mechanical force, or by a combination of these. Hence, for people all mechanical forces feels exactly the same whether they cause coordinate acceleration or not. For objects likewise, the question of whether they can withstand the mechanical g-force without damage is the same for any type of g-force. For example, upward acceleration, for example, increase of speed when going up or decrease of speed when going down, on Earth feels the same as being stationary on a celestial body with a higher surface gravity. Again, one should note that gravitation acting alone does not produce any g-force. G-force is only produced from mechanical pushes and pulls. For a free body, one that is free to move in space, such g-forces only arise as the inertial path that is the natural effect of gravitation, or the natural effect of the inertia of mass, is modified. Such modification may only arise from influences other than gravitation. Examples of important situations involving g-forces include: the g-force acting on a stationary object resting on the Earth's surface is 1g, upwards, and results from the resisting reaction of the Earth's surface bearing upwards equal to an acceleration of 1g, and is equal and opposite to gravity. The number 1 is approximate, depending on location. The g-force acting on an object in any weightless environment such as free fall in a vacuum is 0g. The g-force acting on an object under acceleration can be much greater than 1g. For example, the dragster pictured at top right can exert a horizontal g-force of 5.3 when accelerating. The g-force acting on an object under acceleration may be downwards, for example when cresting a sharp hill on a roller coaster. If there are no other external forces than gravity, the g-force in a rocket is the thrust per unit mass. Its magnitude is equal to the thrust-to-weight ratio times g, and to the consumption of delta v per unit time. In the case of a shock, for example, a collision, the g-force can be very large during a short time. A classic example of negative g-force is in a fully inverted roller coaster which is accelerating, changing velocity, toward the ground. In this case, the roller coaster riders are accelerated towards the ground faster than gravity would accelerate them, and are thus pinned upside down in their seats. In this case, the mechanical force exerted by the seat causes the g-force by altering the path of the passenger downward in a way that differs from gravitational acceleration. The difference in downward motion, now faster than gravity would provide, is caused by the push of the seat, and it results in a g-force toward the ground. All coordinate accelerations, or lack of them, are described by Newton's laws of motion as follows. The second law of motion, the law of acceleration, states that F equals ma, meaning that a force F acting on a body is equal to the mass m of the body times its acceleration a. The third law of motion, the law of reciprocal action, states that all forces occur in pairs, and these two forces are equal in magnitude and opposite in direction. Newton's third law of motion means that not only does gravity behave as a force acting downwards on, say, a rock held in your hand, but also that the rock exerts a force on the earth, equal in magnitude and opposite in direction. In an airplane, the pilot's seat can be thought of as the hand holding the rock, the pilot as the rock. When flying straight and level at 1 g, the pilot is acted upon by the force of gravity. His weight, a downward force, is 725 newtons, 163 pound forces. In accordance with Newton's third law, the plane in the seat underneath the pilot provides an equal and opposite force pushing upwards with a force of 725 n, 163 pound forces. This mechanical force provides the 1.0 g-force upward proper acceleration on the pilot, even though this velocity in the upward direction does not change. This is similar to the situation of a person standing on the ground, where the ground provides this force and this g-force. If the pilot were suddenly to pull back on the stick and make his plane accelerate upwards at 9.8 meters per second the total g-force on his body is 2g, half of which comes from the seat pushing the pilot to resist gravity, and half from the seat pushing the pilot to cause his upward acceleration, a change in velocity which also is a proper acceleration because it also differs from a free-fall trajectory. Considered in the frame of reference of the plane, his body is now generating a force of 1,450 n, 330 pound forces, downwards into his seat, and the seat is simultaneously pushing upwards with an equal force of 1,450 n, 330 pound forces. Unopposed acceleration due to mechanical forces, and consequentially g-force, is experienced whenever anyone rides in a vehicle because it always causes a proper acceleration, and, in the absence of gravity, also always a coordinate acceleration, where velocity changes. Whenever the vehicle changes either direction or speed, the occupants feel lateral, side to side, or longitudinal, forward and backwards, forces produced by the mechanical push of their seats. The expression 1 gram equals 9.80665 meters per second 2 means that for every second that elapses, velocity changes 9.80665 meters per second. 35.30394 kilometers per hour. This rate of change in velocity can also be denoted as 9.80665 meter per second, or 9.80665 meters per second too. For example, an acceleration of 1 g equates to a rate of change in velocity of approximately 35 km per hour, 22 miles per hour, for each second that elapses. Therefore, if an automobile is capable of braking at 1 g and is traveling at 35 km per hour, 22 miles per hour, it can brake to a standstill in 1 second and the driver will experience a deceleration of 1 g. The automobile traveling at 3 times this speed, 105 km per hour, 65 miles per hour, can brake to a standstill in 3 seconds. In the case of an increase in speed from 0 to v with constant acceleration within a distance of s, this acceleration is v2/2s. Preparing an object for g-tolerance, not getting damaged when subjected to a high g-force, is called gardening. This may apply to, for example, instruments in a projectile shot by a gun.
Human tolerance of g-force.
Human tolerances depend on the magnitude of the g-force, the length of time it is applied, the direction it acts, the location of application, and the posture of the body. 350. The human body is flexible and deformable, particularly the softer tissues. A hard slap on the face may briefly impose hundreds of G locally but not produce any real damage. A constant 16 G for a minute, however, may be deadly. When vibration is experienced, relatively low peak G levels can be severely damaging if they are at the resonance frequency of organs and connective tissues. To some degree, G tolerance can be trainable, and there is also considerable variation in innate ability between individuals. In addition, some illnesses, particularly cardiovascular problems, reduce G tolerance.
Vertical axis g-force.
Aircraft pilots, in particular, sustain G-forces along the axis aligned with the spine. This causes significant variation in blood pressure along the length of the subject's body, which limits the maximum G-forces that can be tolerated. Positive, or upward G, drives blood downward to the feet of a seated or standing person. More naturally, the feet and body may be seen as being driven by the upward force of the floor and seat, upward around the blood. Resistance to positive G varies. A typical person can handle about 5 G, 49 meters per second 2, meaning some people might pass out when riding a higher G roller coaster, which in some cases exceeds this point, before losing consciousness, but through the combination of special G suits and efforts to strain muscles, both of which act to force blood back into the brain, modern pilots can typically handle a sustained 9 G, 88 meters per second 2, see high G training. In aircraft particularly, vertical G-forces are often positive, force blood towards the feet and away from the head. This causes problems with the eyes and brain in particular. As positive vertical G-forces progressively increased, such as in a centrifuge, the following symptoms may be experienced. Grey out, where the vision loses hue, easily reversible on leveling out. Tunnel vision, where peripheral vision is progressively lost. Blackout, a loss of vision while consciousness is maintained, caused by a lack of blood to the head. GLOC, a loss of consciousness. LOC stands for loss of consciousness. Death, if G-forces are not quickly reduced, death can occur. Resistance to negative, or downward G, which drives blood to the head, is much lower. This limit is typically in the 2 to 3 G, about 20 meters per second 2 to 30 meters per second 2, range. This condition is sometimes referred to as red out, where vision is literally reddened due to the blood-laden lower eyelid being pulled into the field of vision. Negative G is generally unpleasant and can cause damage. Blood vessels in the eyes or brain may swell or burst under the increased blood pressure, resulting in degraded sight or even blindness.
Horizontal axis g-force.
The human body is better at surviving G-forces that are perpendicular to the spine. In general, when the acceleration is forwards, subject essentially lying on their back, colloquially known as eyeballs, and a much higher tolerance is shown than when the acceleration is backwards, lying on their front, eyeballs out, since blood vessels in the retina appear more sensitive in the latter direction. Early experiments showed that untrained humans were able to tolerate a range of accelerations depending on the time of exposure. This ranged from as much as 20 G for less than 10 seconds, to 10 G for 1 minute, and 6 G for 10 minutes for both eyeballs in and out. These forces were endured with cognitive facilities intact, as subjects were able to perform simple physical and communication tasks. The tests were determined to not cause long or short-term harm, although tolerance was quite subjective, with only the most motivated non-pilots capable of completing tests. The record for peak experimental horizontal G-force tolerance is held by acceleration pioneer John Stapp, in a series of rocket sled deceleration experiments culminating in a late 1954 test in which he was clocked in a little over a second from a land speed of Mach 0.9. He survived a peak eyeballs out force of 46.2 times the force of gravity, and more than 25 G for 1.1 seconds, proving that the human body is capable of this. Stapp lived another 45 years to age 89, but suffered lifelong damage to his vision from this last test.
Short-duration shock and jerk.
Short-term shocks may be caused by impacts, drops, earthquake, or explosion. Shock is a short-term transient excitation and is often measured as an acceleration. Very short-duration shocks of 100 G have been survivable in racing car crashes. Jerk is the rate of change of acceleration. In SI units, jerk is expressed as ms3.
Other biological responses to G-force.
Recent research carried out on extremophiles in Japan involved a variety of bacteria including E. coli and Paracoccus denitrificans being subject to conditions of extreme gravity. The bacteria were cultivated while being rotated in an ultracentrifuge at high speeds corresponding to 403,627 G. Paracoccus denitrificans was one of the bacteria which displayed not only survival but also robust cellular growth under these conditions of hyperacceleration, which are usually only to be found in cosmic environments, such as on very massive stars or in the shock waves of supernovas. Analysis showed that the small size of prokaryotic cells is essential for successful growth under hypergravity. The research has implications on the feasibility of panspermia.
Typical examples of G-force.
Including contribution from resistance to gravity. Plus directed 40 degrees from horizontal.
Measuring G-force using an accelerometer.
An accelerometer, in its simplest form, is a damped mass on the end of a spring, with some way of measuring how far the mass has moved on the spring in a particular direction, called an axis. Accelerometers are often calibrated to measure G-force along one or more axes. If a stationary, single-axis accelerometer is oriented so that its measuring axis is horizontal, its output will be 0 G, and it will continue to be 0 G if mounted in an automobile traveling at a constant velocity on a level road. When the driver presses on the brake or gas pedal, the accelerometer will register positive or negative acceleration. If the accelerometer is rotated by 90 deg so that it is vertical, it will read +1 G upwards even though stationary. In that situation, the accelerometer is subject to two forces, the gravitational force and the ground reaction force of the surface it is resting on. Only the latter force can be measured by the accelerometer, due to mechanical interaction between the accelerometer and the ground. The reading is the acceleration the instrument would have if it were exclusively subject to that force. A three-axis accelerometer will output 0 G on all three axes if it is dropped or otherwise put into a ballistic trajectory, also known as an inertial trajectory, so that it experiences free fall, as do astronauts in orbit. Astronauts experience small tidal accelerations called microgravity, which are neglected for the sake of discussion here. Some amusement park rides can provide several seconds at near 0 G. Riding NASA's Vomit Comet provides near 0 G for about 25 seconds at a time.